So today we're going to take a look at the Blossom algorithm, which is an algorithm for finding the maximum pairing of a graph, right? So let's define exactly what that problem means, right? So if a graph is defined as a set of vertices and edges, the matching is going to be a subset of the edges of the graph such that none of these edges share a vertex together. So for example, if we had the graph, let's say A, B, C, and let's say D. Now, and let's say these are the edges here. Now, one possible pairing could be A and C and B and D. So the set M of these matches would be AC and BD. Now, this set here is not a matching because these two edges share the node A, so that is not a valid matching. Now the problem we have is to find, given a graph, we want to find the, we want to find the maximum pairing, right? And the maximum pairing is defined as it will be a maximum matching if there exists no other matching that contains more edges. So in the example we had, that is in fact the maximum matching because there's no other way that we can get a matching set that has more than that, right? So I'm going to pass it over to Eddie to continue the explanation.
So now let's look at what's augmenting path. So let's say we have a graph that goes like that. An augmenting path is a path that has alternating matches and unmatches, and both of the rare ends of that augmenting path has to be a free node. So what that means is if I have these two paired up and I have another node here and these two are paired up, so we have a sequence of unmatch, match, unmatch, match, and unmatch, and both of the end nodes are not matched. So that's when we say the path is augmenting.
It's an augmenting path, and these nodes are called external.
Yeah,
or exposed nodes.
All the nodes in the graph that are not a part of the match are called exposed nodes.
Yes.
Now let's look at what's Blossom. So let's say a graph has an odd length cycle. So let's say it's a 5-node cycle here, and it has some other nodes outside of it. So this cycle is called Blossom. And the nodes that are on the external side of the cycle are called stem. Or the edges that are on the outside of the graph are called stem.
Perfect. And now the reason this is useful is because the strategy that we will employ is that we will iterate the graph to find these augmenting paths. Because whenever we do find the augmenting path, what we can then do is rearrange the set of pairings. So whatever was paired before, we unpair, and whatever was not paired, we do pair. And what we'll find is that the number of pairings increase by 1. So whenever we have an augmenting path, the number of pairings increases by 1. It is a little bit different whenever there is an odd length cycle, and that will be treated as differently. So we also are identifying whenever a blossom occurs in the algorithm. So here we have some high-level pseudocode to explain this. So this is the high-level function. We'll start with the set, right, of all the pairings that's initialized to the empty set. And while we look through this graph and we find an augmenting path, we then carry out this operation to augment that path and increase the number of matchings by 1. And we repeat however many times that is possible. And once that is not possible, then it is in fact the case that we have found the maximum pairing because there's no other possible augmented path. So this is thus the optimal solution. And that is why this is also an optimal algorithm. And in order to find an augmenting path, I can actually create another example. Okay. So here we have drawn a random graph, and what the first step is, get a random vertex. For example, let's say we pick this one. Then we will check its neighbors in no particular order to a BFS or a DFS. And let's say I found this one, it is unmatched, so thus I will match them and get that augmented path. Then I will pick another vertex at random. So let's say we picked this one here. Now I will check its neighbors. In this case, it's this one. It's not matched, so let's go ahead and match them. Now, say that I picked this node here. I will check its neighbors, and there are two cases. The case where the neighbor is not matched, and in which case we can just match them. And the other case is where whenever there's a neighbor that is matched. So let's say that this check happened first. What I will do in that case is I will actually check whatever that neighbor is matched to, and I will continue the breadth first search from that node. So in this case, I go to this node and I see that it has has nowhere else that I can go, so that's done. So I go back and I proceed with my breadth first search on this initial node, and I get that one. So now I have this, and the only remaining node here now that I can pick is this one. I check the neighbor, it's already matched, so I will check whatever is paired to that neighbor, and it has nowhere else to go. So this is done. And once now this has returned with no new augmented path, we know that we have found the optimal solution, and we'll move forward with that.
So now let's look at a case which has an odd length cycle, which we call blossom, as we saw earlier, and it also has a stem that's extending outwards. So the reason that we're looking at this case is to show why the algorithm that we were talking about earlier does not hold in this case and would not produce the expected output. So let's say we start at this node, and let's call it 1, and we try to match it with the neighboring nodes. So let's say we match it with the one here, and we make our first match. Now let's pick another node in the graph. Let's say we pick this, and we try to match it with its neighbors. So these are the two neighbors that it has, but let's say it's matched to the one here. Now let's look at another exposed node. So let's say we pick this, which is our third node, and let's say it's matched with the one here. Now we have 3 matches already. Now let's try to match another one. Let's say we pick the 4th node, which is this, and try to make matches. So what happens is, when we try to make a match with its neighbors and the neighbors already a part of the match, we move forward to the next node and try to find a node that's not already matched. So let's try this. We arrive at node 1. Since it's already matched, already matched, we move forward to the node that's matched to, and try to move forward in graph. So now that we're here, we will try to find node in its neighbors. So these are the 2 neighbors that it has. So let's say it chooses the one on the left. So we arrive at this, and by the similar logic, since it tries to find nodes forward in the graph, or the one that's matched to it, it will arrive at this node, and applying the same logic, it will return back to the same node, which tells us that the graph has a cycle and we need to accommodate this case. So how we do that is, whenever we detect a cycle, we convert this cycle, or think of this cycle as just one single vertex, and move forward. And this process is called contraction. So let's see how that works. So let's contract this cycle into a single vertex that will look like that, and draw the rest of the graph. And this is our 4th node where we started. Once we contract, we start over the process again and try to find the number of matches here. So let's say we start node 4 again and try to make a match. The node 4 has its neighbor this node, so we make our first match, and then we go ahead and try to pick another exposed node, and we could pick anything. So let's just say we pick this node 5 and try to make a match. It has just one neighbor, so we'll make this match. These are the only 2 matching that's possible in this graph. So once we are done making matches, we move forward to the next step, which is lifting the contraction. So how we do that is, we start by drawing the graph again so that it's simpler to understand. This is what we had. And in the new graph, we have this as a match which wasn't present earlier before contraction. And we have two nodes running here. And this is the new match that we made in the contraction state. So once we have this, all the matches in the cycle will get flipped. So the one match that we had between these two nodes would be flipped and moved over to the next node. So this is a new match that we formed, and the one that was here will also get flipped and moved over. So these two will be matched in the end. So in this example, we move from having 3 matches to 4 matches. And this is how we accommodate odd length cycle graph into this algorithm and find the most optimal solution.
Perfect. And the reason that we do that is because if we were just follow the algorithm mentioned before, on non-bipartite graphs, that could either end in an endless loop or returning a solution that's not optimal. So when we introduce cycles, we introduce the cycle detection and performing that contraction as we saw here, to treat it as a single node and carry out the algorithm. And then once we're done with finding all the pairings for that new graph, we then expand the blossom and we'll return with the full solution. And so looking now at the time complexity for this, so if you think about it, if we look at the time complexity for this algorithm, right? So let's think of the brute force approach, what that would mean. It would mean we'd have to look at every possible subset of this graph. And every possible subset of the graph is given by, well, the subset is some collection of edges. So let's say we have edge 1 up to edge n. And so every possible subset can either have a certain edge, E1, E2, up to En. So for every edge, I have the option to include it or not include it. So the total amount of subsets is 2 to the number of edges. So that's an exponential time complexity. But with the blossom approach, what we have is that, so we start the algorithm at every vertex, so that's V, and for every vertex, we then check all of its neighbors. And the amount of neighbors that it has will certainly be less than the total number of edges in the graph. So then that's V times E on the worst case. And then on the worst case, we can do the contract and expansion operations we mentioned up to V times, right? So we'll add another term V here. So this is E times V squared, which is polynomial time, and it's exponentially better than the naive approach.